We'll start at 9 a.m. in about 3.5 minutes.
Does 9.5 have multiple sections? Does 9.5 have multiple sections?
We're just going to cover one day, and then it will be part of the review that we do next week. Today we'll be in section 9.5 on linear differential equations. Test 2 will be 1 week from today on October 2nd. We'll have that proctored on Zoom again. The sections to get ready for test 2 are 7.7, 7.8, sections 8.1, 8.2, 8.3, and 9.3 and 9.5. So we should have quite a bit of time to review for test 2 next week. But for now, we'll start section 9.5. Notice that I included one more problem from 9.3, number 48. It's a mixture problem. And then these 5 problems from 9.5. We begin with a definition. A first-order linear differential equation can be written in the form dy dx plus p of x times y equals q of x, where capitals P and Q are continuous functions on a given interval. So an alternative way to write this, instead of dy dx, you might see y prime. And then instead of p of x, you might see just p, but I'll write p of x just to remind you that it's a function of x equals q of x. And a word to pay attention to here is that a first order linear differential equation can be written in that form. You'll often encounter first order linear differential equations that are not in this form, but you'll want to be able to put it into that form so that we can solve it. So that's what this next paragraph is about. If a first order linear differential equation is not in the form above, then the first step before solving the equation is to write the equation in that form. Okay, so according to the authors of the textbook, every first order linear equation can be solved. So we'll follow these steps. First, we make sure that it's in that form, dy dx plus p of x times y equals q of x. Then we multiply both sides of that equation by what is called the integrating factor function, capital I of x. And it's determined by raising e to the integral of p of x dx, where p of x is the function of x that we're multiplying by y in this form. The book takes about a page or so to show you how this integrating factor is derived. We'll not go over that in class, but it's pretty easy to follow. You might want to read that. But for now, just remember, when we have a first order linear equation in this form, we're going to multiply every term on both sides by the integrating factor. So we'll go ahead and do that here. So I'm going to write it as e to the integral of p of x dx times dy dx. And then when we multiply the next term by it, I'm going to, whoops, this is plus. I'm going to write the p of x first times e to the integral of p of x dx, and then times y. And then on the right-hand side, I'm going to write q of x times e to the integral of p of x dx. Well, it turns out that the left-hand side is the derivative of a product of functions using the product rule to find that derivative. So I'll write down the function that we compute the derivative with respect to x to. It's just going to be e to the integral of p of x dx times y. If you compute the derivative of this function using the product rule, we get the expression above it. And that should make sense. When you take the derivative of e to the integral of p of x dx, then the derivative of the integral of p of x dx is just p of x. So this should not be foreign to you, with the exception of you might not have seen e to the integral of p of x dx before, but just computing the derivative of this using the product rule gives us this expression. So that's equal to the expression on the right-hand side, q of x times e to the integral of p of x dx. And then we integrate both sides. So when we integrate the derivative of a function, we just get that function. So on the left-hand side, when we integrate, we get e to the integral of p of x dx times y. And on the right-hand side, we'll just write the integral of q of x times e to the integral of p of x dx, and then dx. So for our purposes, this is as far as we're going to take this integral. But the goal is to solve for y. So we'll go ahead and do that. We'll write y is equal to this integral of q of x times e to the integral of p of x dx. And we'll just divide that by e to the integral of p of x dx. And when you compute the integral of the numerator, remember to include the constant of integration. We're not including it here because we haven't evaluated that integral yet. But when you do evaluate that, include the constant of integration. Hey, it's a pretty nice way to solve these kinds of equations. It's pretty simple in general. It will just take a little bit of getting used to, but it's not too bad. So here's an equation, y prime equals x minus y. Well, it's a first order differential equation because the largest derivative, or the first derivative is the only derivative. So it's a first order. Is it first order linear? Well, by linear, they're referring to the exponent on y. The exponent on y is 1, so hence the term linear. So this is a first order linear equation. It's not in the form that we want it yet. So we'll add y to both sides, so we get y prime, which is the same as dy dx, plus 1y equals x. Okay, so this now has this form. It has this form dy dx plus p of x y equals q of x. So for this one, p of x is just the constant 1. And our integrating factor that we're going to multiply both sides of this equation by is equal to e to the integral of p of x dx. But since p of x is just 1, it's just the integral of 1 dx. We know what the integral of 1 dx is. It's just x, so we get e to the x. Okay, so now we're going to multiply both sides of this equation by e to the x. We get e to the x times y prime plus e to the x times y equals x times e to the x. Okay, the next step, the left-hand side is the derivative of a product of two functions. So we can rewrite the left-hand side as the derivative with respect to x of what function? It's e to the x times y. So I should have mentioned, we're assuming y is a function of x. So that should be obvious by this notation, dy dx. Okay, but that's equal to x times e to the x. Okay, the next step. Now we integrate both sides. When we integrate the derivative of a function, we just get the function, right? So the integral of the derivative of e to the x times y is just e to the x times y. And we integrate the right-hand side, which is the integral of x times e to the x dx. I guess we get to review integration by parts. So let's integrate this over here. The indefinite integral of x, e to the x dx. If we use integration by parts and assign u to be x and dv to be e to the x dx, du is dx, and v is e to the x. So u times v is x times e to the x, and then we subtract the integral of v du, which is e to the x dx. So we're just going to get x e to the x minus e to the x. Okay, so over here, e to the x times y equals this, and then plus a constant. So x e to the x minus e to the x plus a constant. The goal is to solve for y, so all we have to do now is divide both sides by e to the x. So when we divide both sides by e to the x, the right-hand side becomes x minus 1, and then plus c. We can either divide by e to the x or multiply c by e to the negative x. It doesn't matter. So I'm trying to decide, what do I want to do? On one hand, I like to divide by e to the x, but it might be more efficient to think of it as c times e to the negative x. Either way is fine. Okay, that's our answer for that part. The next problem, x times y prime minus 2y equals x squared. So it's a first order differential equation. And it's first order linear because y to the first. It's not quite in the form that we want it yet. So remember up here, this is the form that we want it in before we find the integrating factor and multiply both sides. So how do I get it into that form? Well, I want dy dx, or y prime, to be by itself. At the moment, I have x times y prime. So if I just divide every term on both sides by x, we'll get y prime minus 2 over xy equals x. Okay, now it's in the form that we want it. And so the integrating factor, well, in this case, and be careful with the signs in the subtraction. So in this form, we're dy dx plus p of x times y. So the p of x is negative 2 over x, not just 2 over x. See what I mean? So the integrating factor is e to the integral of negative 2 over x dx. Well, we can rewrite the integral in the exponent as, we can write it as e to the negative 2 times the integral of 1 over x dx. So e to the negative 2, and then the integral of 1 over x is the natural log of the absolute value of x. And now what? Using properties of logarithms, negative 2 times the natural log of x is the natural log of x to the negative 2. And e to the natural log of x to the negative 2 is x to the negative 2. X to the negative 2 is just 1 over x squared. Okay, that is our integrating factor. We're going to multiply every term on both sides of this equation by 1 over x squared. Okay, so 1 over x squared times y prime is 1 over x squared times y prime. And then minus 2 over xy times 1 over x squared. This is minus 2 over x to the third y. And then on the right-hand side, x times 1 over x squared is 1 over x. Okay, the left-hand side, why did I write y to the second? I don't know. This is y prime. The left-hand side is the derivative of a product of functions. So which product? It's the derivative with respect to x of a product of functions by the product rule. Well, one thing you can focus on is here we have 1 over x squared times y prime. So we haven't taken the derivative of 1 over x squared yet. We've taken the derivative of y, So by the product rule, if we take the derivative of 1 over x squared times y, using the product rule, we'll get 1 over x squared times y prime minus 2 over x to the third times y. You can verify that. So maybe we can do that if you want, if you're skeptical. So let's check it. Let's use the product rule to take the derivative of 1 over x squared y, where y is a function of x. So I'm going to think of 1 over x squared as x to the negative 2. So when we apply the product rule, we can take the derivative of the function on the left, which is negative 2 times x to the negative 3 times y, and then plus x to the negative 2 times y prime. Or if we rearrange it, it's x to the negative 2 times y prime minus 2x to the negative 3y. If you don't like negative exponents, we can write it as 1 over x squared y prime minus 2 over x to the third y. So is that what we have? Yeah, that's what we have on the left-hand side. So that verifies that the derivative of 1 over x squared y is 1 over x squared y prime minus 2 over x to the third y. And this is equal to 1 over x. Now we integrate both sides. When we integrate the left-hand side, since it's the derivative, we just get the function 1 over x squared y. And the integral of 1 over x, I'll go ahead and write the integral of 1 over x dx. That's the natural log of the absolute value of x plus a constant. The goal is to solve for y. So now all we have to do is multiply both sides by x squared, and we get y equals x squared times the natural log of x plus c times x squared. So this is our solution. Okay, the next one. So the next one, we have t to the second times the derivative of y with respect to t plus 3t times y equals the square root of 1 plus t to the second. So along with dy, dt, and y, we have functions of t instead of functions of x, but it's the same process. Okay, this is not in the form that we want it. The form that we want is dy dt plus p of t y equals q of t. So we can get it into this form simply by doing what?
Dividing by t squared.
Yeah, divide every term on both sides by t to the second. So when we do that, we get dy dt plus 3 over t times y equals the square root of 1 plus t to the second over t to the second. And the integrating factor, capital I of t, our p of t is 3 over t. So the integrating factor I of t is e to the integral of 3 over t dt. We can write the result directly, or if you want to put in a couple of steps, the integral of 3 over t is 3 times the integral of 1 over t dt. And the integral of 1 over t dt is the natural log of t. And what's another way to write 3 times the natural log of t? Yeah, e to the natural log of t to the third. And e to the natural log of t to the third equals t to the third. Yeah. So to summarize, our integrating factor is just t to the third. Okay, so we multiply both sides of this equation by the integrating factor t to the third. And we get t to the third times dy dt plus 3t to the second y. And then on the right-hand side, when we multiply by t to the third, we'll just be left with t times the square root of 1 plus t to the second. The left-hand side is just the derivative of a product of two functions. This one's a little more obvious than the previous ones. So the derivative with respect to t of what function equals this left-hand side? Yeah, t to the third times y. Hey, I'm going to start getting ready to integrate the right-hand side. You can see what's coming when we integrate the right-hand side. Indirectly, we can just use the substitution rule. If u is 1 plus t to the second, then du is 2t dt. So I hope this isn't confusing, but I'm going to write the right-hand side as 1/2 times the square root of 1 plus t to the second times 2t. Because when we integrate, we have to allow for that on the right-hand side. So when we integrate both sides, the left-hand side will just be t to the third times y. And when we integrate the right-hand side, we have this factor of 1/2 out front. I'm going to rewrite the square root of 1 plus t to the second as the quantity 1 plus t to the second to the 1/2. And then we have 2t dt. So the right-hand side will become 1/2 times, well, an antiderivative of 1 plus t to the second to the 1/2 dt, 2t is 1 plus t to the second to the 3/2 divided by 3/2. Dividing by 3/2 is equivalent to multiplying by 2/3. So we get 1/2 times 2/3 times 1 plus t to the second to the 3/2 plus a constant. Just make sense so far? Yes?
Yeah.
Okay. So 1/2 times 2/3 is just 1/3. So we'll cancel those. And the goal is to solve for y. So now we just divide both sides by t to the third. So I'll write this in unsimplified form, but it's okay. It's satisfactory. In the numerator, we'll write 1/3 times the quantity 1 plus t to the second to the 3/2 plus c, all divided by t to the third. If you can read my writing. Okay, the next couple of examples will be initial value problems. So here we have x squared y prime plus 2xy equals the natural log of x, where y of 1 equals 2. So let's make sure we interpret y of 1 equals 2. What's another way of saying y of 1 equals 2? Or, yeah, when x equals 1, y equals 2. That's what that means. When x equals 1, y equals 2. Okay, so what should we do to start with on this one? X squared times y prime plus 2xy equals the natural log of x.
Divide by x squared.
Yeah, we can start by dividing every term on both sides by x squared, right? Because we want, in general, we want the form to be y prime plus p of x, y equals q of x. So in general, we want this form. So if we divide both sides by x squared, we get y prime plus 2/xy equals the natural log of x divided by x squared. So our p of x is 2/x. So our integrating factor, capital I of x, is e to the integral of 2/x dx. So let's go through use the properties of, well, I'm getting ahead of myself. First, let's write it as e to the 2 times the integral of 1/x dx. And the integral of 1/x dx is the natural log of x. And 2 times the natural log of x, so we have e to the 2 times the natural log of x, but the 2 times the natural log of x is the natural log of x squared. And e raised to the natural log of x squared is just x squared. So our integrating factor is x squared. So I'll multiply both sides by x squared, and we get x squared times y prime plus, see, x squared times 2/x is 2x times y. And then on the right-hand side, x squared times the natural log of x over x squared is the natural log of x. So is there anything that jumps out at you as sort of being strange? Yeah, this is exactly what we started with. So that just means that the equation we started with is already ready. It's already ready to be integrated, right? Because the left-hand side is the derivative of a function. So sometimes that happens. It's okay.
A little embarrassing.
It's more fun when you go through the process and realize, oh, I could have saved myself some work. But if you don't go through that experience, you might not remember it. So, okay, so what function is the left-hand side the derivative of? Yeah, x squared y. If you take the derivative of x squared y using the product rule, you get x squared times y prime plus 2x times y. And that equals the natural log of x. And then we integrate both sides. When we integrate the derivative of a function, we just get the function. So the left-hand side is x squared y. And the right-hand side is the integral of the natural log of x dx. So I think during the first week, first couple of days, we learned how to find the integral of the natural log of x. So if you don't remember it, we can find it using integration by parts. So let's just do that. Integrate the integral of the natural log of x dx by parts. If we assign u to be the natural log of x and dv to be dx, then du is 1 over x dx, and v is x. So u times v, we get x times the natural log of x, and then minus the integral of v du, which is x times 1 over x dx. But x times 1 over x is just 1, so it's minus the integral of dx, and so that's just x. So we get x times the natural log of x minus x. Okay, so we get x squared y equals this antiderivative plus a constant. So x times the natural log of x minus x plus c. And then divide everything on both sides by x squared because we're solving for y. So divide every term on both sides by x squared, we get y equals the natural log of x divided by x minus 1 over x plus c over x squared. Then we remember the initial conditions. So we want to find c using the fact that y of 1 equals 2. Okay, so we replace y with 2. Replace every x with 1. We get the natural log of 1 divided by 1 minus 1 over 1 plus c over 1. The natural log of 1 is 0. So that leaves us with 2 equals negative 1 plus c. So add 1 to both sides. C is equal to 3. Okay, so I'll squeeze in the solution here. Y equals the natural log of x over x minus 1 over x plus 3 over x squared. So this is our solution. Okay, the next one, t to the third dy dt plus 3t to the second y equals cosine of t. And the initial condition, y of pi equals 0. So what should we do to start with on this one?
Divide by t cubed.
Okay, divide every term on both sides by t to the third. What?
Or is this equation already a derivative that we can?
What did you say?
I'm trying to figure my words, I'm getting simple. Can we
So-
already turn that into a derivative product of functions? So, can we already turn that function on the left-hand side of the equation into a derivative of a product of two functions?
Yeah,
Yeah, the question was, is the left-hand side already the derivative of a product of functions? The answer is yes. I was hoping no one would catch it so we could experience it once again, you know. But yeah, the left-hand side is the derivative of a function, of a product. So the derivative with respect to t of what function? T to the third y by the product rule, right? So we saved ourselves a little bit of work. And now we can integrate both sides. So the left-hand side, when we integrate the derivative of a function with respect to t, we just get the function t to the third y. Integrate the right-hand side, we get sine of t plus a constant. And now we can divide both sides by t to the third. So we get y equals sine of t plus c, all divided by t to the third. And then the initial condition, when t is pi, the y value is 0. So we replace y with 0, replace t with pi. So in the numerator, we have sine of pi plus c divided by pi to the third. Sine of pi is 0. So 0 plus c divided by pi to the third. So that must mean that c is also 0, right? Okay, so since c is 0, then our solution is just y equals sine of t divided by t to the third. Okay, that brings us to a couple of mixture problems from section 9.3. So these mixture problems are, once you've done a few, then you'll know how to do them. So this one says a tank contains 1,000 liters of brine with 15 kilograms of dissolved salt. Pure water enters the tank at a rate of 10 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. Find the amount of salt in the tank after t minutes. Okay, so I'm going to define capital S of t to be the amount of salt measured in kilograms that's in the tank after t minutes. So amount of salt measured in kilograms in the tank at time t, where t is measured in minutes. Okay, and the information that's given has to do with the rate at which salt is entering and leaving the tank per minute. So in other words, we're given information about the derivative of S with respect to T. So there's a rate of salt coming in, being pumped into the tank, and then there's a rate that measures how fast it's being pumped out. Right? Rate in minus rate out. Okay, so we're told that pure water enters the tank at a rate of 10 liters per minute. So that's giving us information about the amount of salt that's being pumped into the tank. So how much salt per minute is being pumped in? 0, because it's pure water, right? So the rate at which salt is being pumped into the tank is 0 liters per minute. Well, 0 times 10 liters per minute, if you want to be more technical. But 0 times that is just 0. But the solution that's being taken out of the tank or drained from the tank isn't pure water, it has salt in it. So it's also being pumped out at 10 liters per minute. How do we determine what amount of 10 liters is being pumped out per minute? Well, at any time t, the decimal form of the percent of salt that's in the tank can be found by dividing the amount of salt that's in the tank by 1,000. Right? The total tank contains 1,000 liters. It's not pure salt, but it has some salt in it. If you divide S of T by 1,000, where S of T just represents the amount of salt that's in the tank at time t, that quantity divided by 1,000 gives you the decimal form of the percent of salt that's in the tank at that instant. So if we multiply S of T divided by 1,000 times 10 liters per minute, this tells us how much salt per liter is leaving the tank per minute. Because S of T divided by 1,000 is the decimal form of the percent of salt that's in the tank, which is being drained at 10 liters per minute. Does that make sense? Okay, so we'll simplify this a little bit. ds dt, we'll just write it as negative S over 100. And we know that the units are liters of salt per minute. Okay, but this is our differential equation. This one is separable. So we can separate the variables. We can write this as ds over s equals negative 1 over 100 t. We are out of time, but probably by now you've had experience solving this kind of equation. So that's all for today.
these basically related rates problems, or are they kind of different?
What was?
Related rates problems?
They're similar, yeah.
Okay.
We're not really talking about two different rates. There's just,
Okay.
it's just like one rate, so they can write it as a differential equation.
Okay.
But some of the things are applicable.
So I just had a general question, and I think I have